So this time we're going to be talking about simple and fractional distillation. So the scenario for using distillation is I've got a mixture of two reasonably volatile liquids. Volatile means that they're easily vaporized. I apply a little bit of heat and they go into the gas form. Ideally, the two liquids have boiling point differences of at least 10 degrees Celsius. The bigger the difference in boiling point, the better this is going to work in terms of distillation. But it is a separation technique, and that's what we're going to do here. There's two types that we're going to perform. The first week, we're going to perform what's known as simple distillation, and you're going to see why it's called simple distillation. It's the most bare bones, basic setup for distillation, and that's going to be followed the following week by fractional distillation, which in theory should work better, and we're going to talk about the reasons why briefly in the theory section of this discussion. So let's in fact talk about the theory, and at the same time I'm going to scroll down a little bit pretty quick here, and I'm talking about the theory, and here's a little picture to talk about the theory. This is your basic simple distillation setup, and we've got a round bottom flask that contains an issued sample mixture. So when you're ready to start this experiment, there's going to be a cart full of unknowns to choose from. Make sure that when you get that unknown mixture back to your bench, as always, you write down the number of that unknown mixture. And this is going to fill your round bottom flask mostly full, at least 2/3 full. Ideally, you don't want the round bottom flask too full, otherwise you can start to get problems with boiling over and such. This little heating device down here, I don't think we've used these before, maybe we have, but they're called heating mantles, and these are going to be located in the back, far back corner of the laboratory, and they're going to require a controller and all this kind of stuff. We don't use hot plates for this experiment. We use heating mantles because they wrap around the round bottom flask a lot more effectively. Round bottom flask, this is called a three-way adapter is the next thing. And a temperature goes through the thermometer adapter, and the placement of the thermometer bulb is really critical because you want that top of that thermometer bulb to be right in line with the three-way adapter, and that's the perfect positioning, so make sure you get that set up correctly. This is called a condenser, and the condenser has two chambers inside of it. There's an outer chamber which water comes in on the low side here and exits the high side. We're going to be using a lot of water for this, and hopefully you're using cold water because the inner chamber has volatile gases that are going to hit this condenser, and with that cold outer jacket, they're going to condense and eventually drip down into this graduated cylinder. So here's how the theory works. You've got your mixture. The lower boiling point compound is going to start to volatilize a little bit easier than the other one, and it's going to start to become a gas and travel upwards, hit the thermometer, and you are going to take a thermometer reading every milliliter of distillate that you're collecting, and then it's going to start to curve downwards, hit that condenser. It's still a vapor at this point, but as soon as it hits the condenser, it condenses into a liquid, and the liquid starts to drip down, and it collects into this grad cylinder. So we're going to be monitoring a couple of things while we do this experiment. One is we're going to look at the temperature the whole time, and later make a graph based on those results. The second thing we're going to monitor is how many milliliters of distillate we're collecting. This is the traditional approach, and that's important too because once we get to the 4 milliliter mark of distillate collected, you are going to take a sample of the distillate using a GC vial and cap it up right away. And then later, once you get to 20 milliliters of distillate collected, you're going to take a second sample, and that's 20 milliliters later, and that's also going to go into a GC vial. So with the temperature data, later you make a graph, and the graph should, in theory should go like this, ideally, where milliliters of distillate collected and temperature ideally goes something like this. It rises really rapidly, and then it levels out, and then it goes up again and levels out again. This region right here, the first flat region, is where the first component is located. And based on what that temperature is, you're going to be able to identify what that first component is. And then, of course, if this works out well enough, this is the second component. And this flat region right here is its temperature, and you identify that component by its boiling point temperature too. So this is the boiling point of this first component, the boiling point of the second component. Now, simple distillation may not work out perfectly like this, and that's why we're also going to do fractional distillation. And let's talk about that now. So fractional is a little more sophisticated at separating mixtures because You still set up the simple distillation setup, except that you're going to put in what we call a fractionating column between the round bottom flask and this three-way adapter. So one type, the more common type that we have, is just an empty column which you pack with steel wool. And as the vapors start to heat up and travel up the tube, they're going to hit this steel wool and automatically condense right onto the steel wool surface. But it's so hot in there that they eventually revolatilize, and they keep doing that over and over and over again as they travel up the tube. And you're getting, a lot of bang for your buck in terms of separation, because they just keep recondensing, separating, volatilizing, and all the way up the tube till eventually, of course, hit this three-way adapter, hit the condenser, they condense, they drip into a liquid. And once again, you're monitoring the temperature the whole time, and you're monitoring the distillate collected. As a reminder, you need to collect at 4 milliliters of distillate collected and also 20 again. So in the end, after 2 weeks worth of work, you're going to have 4 samples that we're going to analyze by GC. GC stands for gas chromatography. That's going to be the ultimate proof as to how well this separation is. Once again, if you were to make a graph of this data, the ideal situation is temperature versus milliliters distillate collected. Ideally, the profile looks like fast rise, level out, fast rise, level out. And again, this is the boiling point temperature, the first component, and the boiling point temperature, the second component. And what's probably going to happen, we hope, is that fractional distillation is going to produce a cleaner graph in that regard. So it'll be easier to identify the two components. It doesn't always work out that way. Sometimes I've seen simple distillation work better, but that's in theory what should happen if we have a perfect experiment. So 2 weeks worth of work, simple and fractional distillation. I'm going to give you just a few more details about the experiment before I start showing you the techniques in terms of videos. So again, the first week is simple distillation. Second week is fractional distillation. You're going to monitor that temperature while conducting the distillation using either a standard thermometer or some of you might be lucky enough to use one of our verniers. So these are the digital thermometer probes. They have to be high temperature. We can't use the standard ones. But anyways, that's a lot simpler. And we don't monitor by distillate collected. We monitor by time. And that also creates a graph automatically. So it's really slick. So only a couple of you are going to be able to use that. I think we only have about 5 of those at this point. So don't forget to take a sample at 4 milliliters as you're collecting distillate, but also 20 as well. Another thing you want to watch out for is leaks in your setup. So when you first get set up, it's wise to call me over and make sure that we don't have any leaks. Because if you have a leak, you're not going to be able to get to the 20 milliliter mark. It's going to be all leaking out the sides, and it's going to be really stinky. All right, so we're going to check those results for that simple and fractional distillation using gas chromatography. That's going to be a separate talk about how gas chromatography works, but that's what's going on in this experiment. In a lot of ways, this is a much simpler experiment compared to, say, chromatography, which we recently wrapped up. Okay, so as usual, I'm going to show you the laboratory techniques as videos and take a watch. I was about to say take a listen, but watch that video and hopefully you'll be ready by Friday. We're setting up for a distillation, 2 types of distillation. We're going to do what's known as simple distillation and fractional distillation. You are going to truly grab an unknown mixture, although what I have here, I know what the components of this mixture are. This is hexane and toluene mixed together in 50-50 proportions, but you're truly going to have an unknown mixture. And you're going to get a chance by distillation to separate these 2 components of this mixture away from one another, determine their boiling points, and identify what those compounds are. I've already done this, so I know what this mixture is, fine, but I've already taken 28 milliliters, according to the procedure, 28 milliliters of this into a 50 milliliter round bottom flask that you can just barely see in this video. In addition to that, I've got an iron ring, which are available in the cubby holes in the front part of the laboratory. Heating mantles, this is what we always use for distillation. These are available in the back corner of the laboratory. You're going to need a controller for that heating mantle, also in the back corner of the laboratory. And the most important clamp in the entire distillation setup is this one. This is a 2-finger clamp. Don't use the 3-finger clamps. This 2-finger clamp is going to wrap around this round bottom flask. And in the simple distillation setup, this 3-way adapter goes on top of this. But before I move on to the 3-way adapter, I almost forgot to mention that there's also a boiling stone added to this round bottom flask, which is critical. Don't forget the boiling stone. It prevents rapid boiling, or violent boiling, I should say, of the mixture. So 50 milliliter size round bottom flask, 28 milliliters of the mixture, boiling stone, don't forget the boiling stone. Three-way adapter for a simple distillation setup. At this point, a condenser is going to go here and a thermometer up top. Let me just say a few things about the thermometer in this setup. This is a standard thermometer. You can find these in the center bench. These are high temperature thermometers, and you should have a thermometer adapter in your drawer. Thermometer adapter is just this small piece of glass with a little grommet at the top. The safe way to put a thermometer into one of these is to grab it real close to the rubber piece and just kind of gently push this through. And we're looking for a very specific height of the thermometer inside the distillation setup. So I've already got this one pre-made. I'm gonna go ahead and slip this into the setup at this point, push this fume hood out of the way real quick. And the way I've positioned this thermometer, the height of it is such that the bottom bulb part of the thermometer, the top part of that bulb, is right in line with the lower part of the three-way adapter. So the positioning of the thermometer is real critical when it comes to distillation. We want to get accurate temperatures because, again, one of the ways we're going to identify the compounds is by boiling point temperatures. It's really critical that you position that bulb correctly. So once again, the top part of the lower bulb is perfectly in line with a three-way adapter. That's what you want for this. Some of you may get a chance to use a digital thermometer. This is a vernier setup. This is called a wide range temperature probe. I'm going to actually use this in the experiment, but I wanted to go ahead and show you the analog version of this setup. This is more traditional. This is kind of the fancy pants way. Now with this one, we're going to do the same thing. We're going to push it through the adapter, and you're going to try to position the end part of this tip in a similar manner to this, where you want maybe the last ½ centimeter of this probe in line with the lower part of this three-way adapter. That's the proper setup for a digital, at least as far as I'm concerned. So. All right, so what else? So this is a simple distillation. Like I said, a condenser goes here. Briefly, I'm going to show you a fractional distillation setup. So instead of actually having that like so, in a fractional distillation, we're going to position one of these guys, which is a fractionating column. And this is going to go right on the round bottom flask, and then the three-way adapter is going to go up top. But as part of the setup for the fractional distillation, we're going to stuff this column with some material, which happens to be steel wool. And the purpose of the steel wool that I'm going to stuff in here is to have the vapors, the volatile components of this mixture, travel up and condense continuously on the steel wool as it travels up the column. So in theory, fractional distillations are always better at separating mixtures versus simple, and we're going to get a chance to prove that with some real data, some hard data. Now, the way to stuff this column with the steel wool is just to take little bits at a time of the steel wool and kind of ram it gently inside this fractionating column. And I've already done this ahead of time. This is not a true fractionating column, but it still works. And you can see I've already stuffed this column with steel wool, such that you don't want it real tight in here. You just kind of want it to go from the bottom to the top. That's a good setup. And again, this is for fractional distillation. So the only difference between simple distillation and fractional is the addition of this little piece. It's also probably going to require that your entire setup be a little bit higher up before you get started, because this column is really tall, as you can see. And so the whole thing ends up being a little bit higher. But let's go ahead and set up for simple distillation. So simple distillation, I've already shown you parts of that. We've got the three-way adapter. I've already positioned the thermometer properly for this setup. I think this is the one. Let me check this. Nope, that's definitely the wrong one. So it's this one. Okay, I'm going to orientate the thermometer so I can easily see the data. All right, so that's that. The condenser, I've already pre-connected the latex tubing, but try to find in the front drawers long enough tubing. I'm going to really be stretching this because I'm a long ways away from the sink, but latex tubing that's long enough and it's going to easily fit over the condenser. The condenser is kind of one of the more important pieces. Let me go ahead and hook this up so we can talk about this. The condenser fits on like this. You'll want to use a Keck clamp to hold this in place so it doesn't slide off. Keep in mind too that you don't need a Keck clamp on this lower part because gravity is going to hold the three-way adapter in place on this part of the setup. This clamp right here is simply just to hold it in place. You do not want to clamp this too tightly. It's just there to kind of stabilize the condenser, because if you have it too tight, I've noticed that this will get pulled out of joint and then you've got leaking vapors the entire distillation setup. Now here's how this works. As we start to heat this mixture, the volatile components, so the lower boiling point compound, which is hexane in this case, is going to boil a little bit sooner than the toluene. As the hexane vapors travel up this setup,
They're going to reach this point right here. Our thermometer is going to register the temperature, which we want, and they're going to start to travel down the condenser. The condenser is a really fancy piece of glassware. It's got two chambers. It's got an outer chamber which the water passes through, and it's got an inner chamber which the gases pass through. As soon as those hot gases hit this part of the condenser, they're going to be cooled immediately by the water that's always passing through the outer water jacket. They condense, they start to drip down, and eventually we collect those drippings, that distillate, as a liquid, and you're going to monitor the process by looking at the milliliter collections, actually. So you got to constantly monitor how many milliliters of distillate you're collecting in this little graduated cylinder. So the procedure will call for also a dripper tip, and that's just simply to guide the distillate into the graduated cylinder. So we're going to clamp that as well so it doesn't fall off. All right, so we've got this all kind of positioned. This is just right so that it's going to drip right into that graduated cylinder, and we're not going to miss in our little collections. Now the procedure, once you get going and start heating this, we're going to gradually collect distillate. You're probably going to get about a total of 20 milliliters of distillate, maybe a little bit more, maybe a little bit less. But the procedure specifically mentions that at about the 4 milliliter mark, so you're watching this the whole time, you're watching the temperature. Every time you reach 1 milliliter of distillate collected, you got to take the temperature. On the digital version, that's pretty simple. On the analog version, you've got to remember to do that. Every milliliter that you collect, you got to read the temperature in Celsius. At the 4 milliliter collection point, what you're temporarily going to do is move this to the side and collect just enough distillate in this tiny little auto sampler vial, which are available in the cart. You're going to collect about a third's worth of distillate in this little auto sampler vial. So we're going to put this on the gas chromatograph eventually to kind of analyze how well we did at the 4 milliliter mark. What we expect after 4 milliliters is mostly hexane in this case, because hexane is the lower boiling point compound, so hexane we think. And then later you put this back, you're collecting more distillate. Later towards the 18 milliliter mark, you're going to switch to a different auto sampler vial, collect that distillate, and that should be mostly toluene at that point because that's the higher boiling point. So we're doing a couple things here. We're not only identifying the components of the mixture, yours is truly an unknown, but we're also going to kind of see how pure we can get these components by distillation, both simple distillation and also fractional distillation. We expect better results from fractional distillation. A couple other things to mention about this setup. One thing I almost forgot to mention is the water, the incoming water supply must enter on the low side of this condenser and exit out the high side. That's the way it's always done. So that's another little bullet point. Don't forget to put Keck clamps here and here, but don't put a Keck clamp here. This is held in by gravity. Try not to heat the setup too fast. If you go too fast with this distillation, you're going to get kind of crummy results on the other side. You won't get clean separation. I mean, the bottom line is we don't expect good separation from simple distillation compared to fractional distillation, but don't go too quick on this. Don't try to rush it, okay? Don't forget to collect your little fractions at the 4 milliliter mark and also the 18 milliliter mark. These are the caps that go on these little vials, so you'll want to cap those as soon as possible. For fractional, again, you're going to pack a column, one of these fractionating columns properly. Don't pack in the material too tightly into this. Don't forget to position your thermometer really correctly. I'm also going to mention one last thing. This is called a Claisen adapter or Claisen adapter, however you want to pronounce that. Sometimes you'll see people actually position this before the three-way adapter, especially when they're doing steam distillations of natural products. Sometimes they get really foamy, and so this acts as an extra trap so you don't get the foaminess coming over in the condenser. But we're going to skip that because this is not a natural product, steam distillation. But otherwise, you can do that if you want to. Okay, so at this point, to complete this distillation, I'm going to take you through the actual data collection. I'm going to switch from an analog thermometer to a digital one, so you can actually see the temperature profile as we do this distillation. We've got our distillation set up and ready to go. I've placed a digital thermometer probe in the setup. We talked about earlier how to position this. We want the tip a little bit below the three-way adapter outlet. I've got my software loaded up. This is Logger Pro. Once again, it's going to monitor the data for us. It should default to the right experiment. We've got time on the x-axis. We've got temperature. We've got time on the x-axis, temperature on the y-axis. Unfortunately, the one thing we're going to have to change before we get started is it usually does not give us enough time to do the data collection. Distillations are going to take upwards of approximately 30 minutes or so. So go up to experiment, data collection is what you're looking for. There's going to be a spot where you can choose minutes, and we're going to go ahead and, just to be safe, we're going to set this to 30 minutes. Let's change it to 45 minutes just to be safe. Now the number of samples per minute is not critical, but probably what we want to do here is we want to change it to a sample, let's see, samples per minute. Let's change it to 10 samples per minute. I think should be fine. Okay, this is set up and ready to go. Unlike the procedure states that we're going to collect a temperature point every milliliter of distillate that we correct. So I just want to make this clear that if you're using a digital probe, we're going to do data collection by time rather than distillate collected. But either way, it's fine. We'll see a data temperature profile. Now what I'm going to do is I'm going to go ahead and start the data collection by just simply clicking the green button here, and that's going to start to log our data. And very quickly I'm going to turn up the temperature on the heating mantle. Now to get this setup going, I'm going to go full blast to get this going, and that's going to heat up the round bottom flask as quickly as I can, and that way once I start seeing, I turned this the wrong way here, I want it on high. That way once I start seeing the dripping, I'm going to scale it back, and ideally what we're looking for is one drip every 2 seconds. That's the perfect amount. So it's on high right now, get it going quickly. As soon as I see the first drop of distillate, we're going to scale it back. Now the last thing, and I almost forgot, the most important thing is to turn on the water supply. So I mentioned before that the water's coming in on the low side, exiting the high side, and just go easy on the water, because I've seen a number of times the water comes out too quickly in the beginning and pushes the hose off. So we want just a kind of a steady trickle of water coming out the high side, and it looks like I've got it nailed. At this point, we're just going to have to wait. We have to be patient. The temperature is not going to show any climbing until the moment the distillate starts coming out of the tube. So we just have to be patient at this point. So I've got a couple of different camera angles, and I've got to be watching this experiment. Like I mentioned before, at the 4 milliliter mark of the graduate cylinder, I'm going to have to take my little auto sampler collections, and so we'll do that when the time comes. Right now I'm scaling the temperature back a little bit. I'm turning the dial down to approximately 3. I gotta really keep an eye on the drip rate in this experiment. I don't want it to go too quickly. If you go too quickly, it wrecks the separation part of it, and that's the most important thing in distillation. We're trying to separate the two compounds. If you rush this, it's gonna be a disaster. Now I'm looking at the temperature now, and it's very quickly rising, which means that we're pretty close to dripping already. And so now I'm gonna scale this back even more. And we're watching for the first drop and making sure that it's about a drop every 2 seconds. Here comes our first drop. I can just see it forming at the end of the dripper tip, or the end of the condenser, I should say. There it is, the first drop. So now at this point, what we're gonna do is we're gonna keep an eye on the total volume of distillate collected. Looks like right now my drip rate is a little bit too fast. I'm gonna turn this back just a hair. What we assume about this experiment, since this is a mixture of hexane and toluene, we're assuming that the distillate that's being collected right now is mostly hexane, and later, once we get towards the end of the experiment, we're going to assume that it's mostly toluene. That's the whole point of distillation. We're going to collect the lower boiling point compound first, the higher boiling point compound second. All right, so I'm close enough to the 4 milliliter mark that I'm going to go ahead and take a sample in an auto sampler vial. So just temporarily move this to the side after the next drop here. And I mentioned earlier that we're looking to collect about, we're trying to make this little auto sampler vial about a third full is the goal. Okay, we've got enough in our little auto sampler vial that we can go ahead and use this in the GC later. So I'm going to cap this up. Make sure you keep track of which sample this was. You'll need to make a note of the fact that this is a simple distillation, but also this is the 4 milliliter mark. Make sure you make a note of that. I'll probably end up having a sign-up list for the gas chromatograph, but this is our first sample. So now we wait. We're going to have to wait till we get about 18 milliliters. If you see you're about to run out of mixture in your round bottom flask and you haven't reached the 18 milliliter mark yet, just go ahead and take a sample at 16 milliliters or 14 or whatever you have to do, but try to get that second sample towards the end of the distillation. Okay, I want to make a small correction in the procedure. I think earlier I mentioned that we're going to take a collection at 18 milliliters. The procedure actually calls for 20 milliliters, so we're now rapidly approaching the 20 milliliter mark. I'm going to go ahead and take another sample. Here's my second little GC vial, auto sampler vial. And once again, I'm going to look for about a third full. Okay, I've got approximately what I need. I'm done with this cap. I'm going to go ahead and collect a little bit more distillate just to make sure that I've leveled out in terms of the second temperature I'm looking for. So remember, the whole idea of this experiment is to identify the two components of the mixture. Yours is truly an unknown, so I want to make sure that I get two separate stable temperatures so I can later identify what the compounds are. All right, so at this point I'm getting low on my original mixture. I want to go ahead and stop the heating process at this point. I'm pretty comfortable with the way this data profile has turned out. I see the upper temperature. I think I can later identify this. So let's turn the heat off, and make sure you turn the heat off well before the round bottom flask goes dry. Otherwise you'll end up burning the original mixture. That's a bad thing. It's really tough to clean burned organic material out of your round bottom flask. So that concludes the entire distillation. We've collected about 22 milliliters at this point. We've monitored the temperature versus time. We've also taken two collections. Our first collection was a simple distillation at the 4 milliliter mark. Our second collection was at the 20 milliliter mark. Let's label these as simple. This is 4, this is 20, and later I'm going to show you how to do the gas chromatograph portion of this.